Fusion energy has long been seen as the holy grail of clean power, a technology that could one day provide abundant electricity with minimal emissions and little long-lived nuclear waste. While that future may still be years away, researchers at the University of Houston are playing a key role in bringing it closer. Our guest today is Dr. Venkat Selvamanickam, professor of mechanical engineering at the University of Houston. He is leading a multi-institution research team studying superconducting magnets, an essential technology that could help make practical fusion energy a reality. Dr. Selvamanickam, welcome to Hello Houston. Thank you for being here today. Now, as Ernie and I were talking about before the show, we both slept through our physics class in high school, so you're going to have to really break this down for us. What exactly are you looking at, and how close are we to fusion energy?
Yeah, first of all, thank you for having me today. Fusion has been around for a while. People have been talking about fusion for a long time. So fusion is a way how the sun and the stars produce energy. Essentially, they fuse hydrogen atoms and produce helium and then produce lots of energy in the process. The thing is that you require extremely high temperatures, about 100 million degrees temperatures to get to create fusion.
Hotter than the sun, right?
Hotter than, essentially the sun's temperature, right? I think, so you need to recreate that conditions on Earth. So how do you do that? So that has been the challenge, an engineering challenge that people have been struggling for the last 30 years. And there are ways to do it. The way you do it is you confine what you call the plasma, and you heat this material to extremely high temperature, like 100 million degrees. It's so hot, it's going to burn through pretty much any container or any vessel that you can put around it. So one way to confine this very high temperature plasma is to use something called superconducting magnets. So use these magnets, and that actually keeps the plasma in place, and then that promotes the reaction between the hydrogen atoms and creates a lot of energy. So the challenge has been that the energy that's produced is always been less than the energy that you put in. Mm-hmm. So what's the point of going through fusion if you're going to waste the energy, right? But there are indications that it's possible to get more power, more energy than what you put in, and that's the excitement.
Let me ask a very basic question, though. We can do it. Should we be doing it? When you're dealing with these kind of temperatures, and we have seen so many disasters along the way in other kind, and people that are regular listeners to the show know I'm always skeptical of humans and their ability to actually do mechanical things, let alone stuff. Is this something we should be playing with?
I believe so, because there are many benefits of fusion. Like you heard before, there is no byproduct, no radioactive waste. Unlike nuclear fission, we are actually breaking atoms and producing energy, and in the process creating radioactive waste. There's no radioactive waste coming out of this. And another great thing about fusion is there's no need for storage. Like we have solar energy, we have wind energy, which is great technologies, but eventually you had to find a way to store them, because when the sun is not shining or the wind is not blowing, there is no way to produce that energy. Whereas fusion is something that's on all the time. And so I think this is a great way to eventually get into a clean energy source which doesn't have the problems of energy storage.
So just from a practical standpoint, what were we talking about size-wise here? I mean, how big would a fusion reactor be, and what size could power what? Because we see these huge nuclear reactors as well as these large, coal plants and other power-producing plants are very large. How big would a fusion reactor be, and what size would power what exactly?
Sure. So they're building actually a fusion reactor in France. It's called ITER, International Thermonuclear Energy Reactor. And that's huge. That's a behemoth, right? And then that's going to be very hard to commercialize as a power plant. But what's happened the last 5 to 10 years is that this concept of something called compact fusion, making the fusion reactors relatively small. It's still large in the size of a school bus, which is still, not, compared to some other large power plants, it's not that big. So, the way this compact fusion can come about is because of the superconducting magnets that I mentioned before to confine the plasma. So using the superconductors like the ones that we are developing at the University of Houston, you can actually generate much higher magnetic fields in these magnets. And now you can actually make the size of the fusion reactor much smaller. And that's been the excitement over the last few years. in this area.
Like what, the size of a building, the size of a bus?
Yeah, size of a bus, yeah,
Okay.
approximately, yeah.
And what would that power?
Yeah, that will provide about 400 megawatts of power. That's a pretty decent size power plant. Yeah.
How much competition is there now? Because I know there's been a huge push for these small modular nuclear reactors coming on. I mean, and I know that other universities are looking at that and trying to expand on how to make these little small compact nuclear reactors.
Right.
How much competition is there versus fusion reactors?
Yeah, I think eventually you need to probably have different types of energy sources, right? There's no one singular answer to this. So while, the advancements are being made in the nuclear fission reactors, I think because of the advantages I mentioned, there's no need for storage, there's no radioactive byproducts. So I think really makes fusion a lot of sense in terms of trying it out, right? Because if we can actually make this to work, of course, it's a huge engineering challenge still ahead of us. I think there will be plentiful amount of energy available because the amount of fuel required for this is much small. You don't require a lot of fuel. It's like I said, it's only the hydrogen isotopes that's required. So I think in all cases, this could really be a wonderful way to have a clean energy source for the future.
Excuse me if this is way too basic, but in trying to understand it. When you talk about magnets and containment, I think about with magnets, you have the positive and the negative sides, and when you put them the wrong ways here, they push against each other as opposed to pull together. Is it that kind of force holding the material
exactly.
in?
Yeah, it is something like that, right? So basically, this is actually a superconducting coil. It's actually think of a big coil that's wound with this powerful superconducting wires. And so essentially what they do is that because the magnetic force is so high, they can actually keep the plasma in place, right? It doesn't allow the plasma to go and hit the walls of this fusion reactor container, right?
Wow, I'm just kind of fascinated by the whole idea. And I know there's been a lot of misunderstandings of magnets all the way from the current president who kind of thinks if they get wet, they stop working. But the beauty of magnets is you don't have to power a magnet, correct?
No, you do have to power the magnet. You do have to power the magnet in this case. But being a superconductor, you don't need much power to power these magnets because that's the beauty of the superconductors. Because, if you use a copper wire to make an electromagnet, you need tremendous amount of power. And that, you could be wasting all their energy in powering the magnet. But as superconductors, they carry electricity with zero resistance. So now you can actually make extremely powerful magnets. You can pass something like 100,000 amperes of current through these magnets, and they can create extremely high magnetic field, something like 200,000 times more than the Earth's magnetic field, and still doesn't require much power to power these magnets.
If the power were to go out, though, if the power failed to the magnets, what happens to the material that it's containing?
Right. So the good thing is the superconductors can actually stay in a superconducting state for some time, because it actually, as long as you keep it cold, right? You need to keep it at relatively low temperature, something like 20 Kelvin, which is about 20 degrees above absolute zero. So it's pretty low temperature. So as long as you keep it at that temperature for some time, so you have some time to recover. And so there's an opportunity to go and fix the problem. Of course, if for some reason the temperature gets too high, then of course, then you will have problems. So there are a lot of work that's being done, engineering work being done to make sure these magnets never something called quench. They never actually exceed the temperature at which point they'll become non-superconducting.
So it sounds like, okay, obviously we understand how fusion works. We understand that these large magnets can create these magnetic fields to contain the material. So what are the practical hurdles making this a reality then?
Right. So a few things. Now, the one of the things that the project that we are working on is actually to look at what happens when these superconducting magnets are exposed to this radiation. What happens is that, as you're producing these, large amounts of energy and helium as a byproduct, we also produce a lot of neutrons. So neutrons, of course, like protons and neutrons, electrons we studied in our physics classes.
I was awake for that.
Okay, good. All right. So these neutrons, they can hit these magnets, and what they can do is that they're extremely going a very large amount of energy, and they can actually displace the atoms in the superconducting magnets. And now the superconducting magnets can start to fail, right? Not stop working immediately, but the lifetime of the magnets will degrade over a period of time. So that's a problem that we're trying to address at the University of Houston.
How not to have the magnets degrade.
That's right. Yeah, when you have this exposure to the neutrons that are generated during the fusion process to make sure these magnets don't degrade, extend the lifetime of these magnets or this fusion reactor to more than 30 years.
Okay. And we are speaking with Dr. Venkat Selvamanickam. He's a professor of mechanical engineering at the University of Houston. If you'd like to join this conversation, please call or text us at 713-440-8870. Now, talking about alternative sources and saying it's important to have, basically a whole portfolio of energy sources, how much more critical is something like this going to be in the age of AI and data centers that are popping up everywhere?
Absolutely, yeah. So that the data centers is consuming so much power, so even probably more power than what we had anticipated we'll be needing the next few decades. So absolutely need to have additional source of energy, right? I think never say everything, right? Wind energy, is wonderful, but it has its own challenges, right? You had to use some permanent magnets, and you had to rely on rare earths coming from China. Solar power is great, but again, there are some challenges with that also. So there is no silver bullet in this energy issue. So until we get to a stage where self-sustaining, that we can actually have sufficient sources of energy, it's very important to really develop these new energy sources so that even though, again, very hard engineering challenges, but if it works, I think this could actually be a big solution for the decades to come.
Being of an age that 3 Mile Island pops into my mind, and I always think of the ultimate disasters that could happen. This kind of material at this heat, broken free, what does it do on this planet?
Right. So the thing is that the heat is, if the fusion process stops, the heat quenches immediately. The heat goes away. So, right, because if it's not something that is going to, if, for example, if something has to trigger this fusion reaction to stop, right? So now everything, it can just stop the process right then and there. So you're not going to have any radioactive waste leakage.
Lava.
No, you're not. Right. So you're not going to have anything like that, right? So the things like the byproduct is like helium, which is like, of course, the helium balloons that you use, and then of course these neutrons, which are usually contained, they actually put in thick blankets in a way to absorb some of these neutrons. Some of the neutrons make it way through the superconducting magnets, but apart from that, there is no additional byproducts that you need to worry about. So so the worst thing that can happen is for example, if there's a power failure, like I mentioned before, and the magnets quench, then you have you don't have power being produced. But no way it is going to be it's not going to be calamity like some kind of leakage, some kind of radioactive damage to the environment.
So it's really exciting, and it really could solve a lot of the problems we're facing if we can get this all to work.
Absolutely, yeah. And the great thing is there are many companies right now. And so this used to be a technology mostly developed at the national laboratories and the universities because such a hard engineering problem. But now, because investors have actually seen an opportunity in this field, especially with compact fusion, so there's been more than $10 billion being invested in many private companies, many of them in the United States. They're actually racing to develop this technology. So that's really the exciting thing about this. Even though it's been around for 30, 40 years, it's now really coming out of the research labs into the commercial companies who are building these fusion reactors.
So in reality then, with what you've just said, how soon will it be impacting our energy grid? Right. How soon can we reap, do you think, benefits?
Some of the early movers are saying that by mid next decade, by early 2030s, you could actually have a functioning fusion power plant.
Wow. Who harnesses then this energy as far as cost? Does it become a public-owned idea, or is it going to be privatized and we're going to be paying still a lot of money for this energy? Does this change the marketplace?
I think there's a potential to change the marketplace in the sense that if you have this abundant energy available at a relatively lower cost, that could actually benefit consumers of energy. So that can bound to happen. And there's a lot of course, government funding that actually went into this, right? Developing all these things. So ultimately, definitely the public would get to benefit from all the research that went into these technologies.
Yeah. Wow, it's fascinating.
Now you're leading a multi-institution team, correct?
Yes.
So who else is on this team that's specifically looking at the superconducting magnets?
Yes, yeah. So we have actually put together a team to look at actually because our expertise at the University of Houston used to develop these materials, the superconducting materials that go into the magnets, right? But then you do need to have a way to bombard these magnets or these materials with the neutrons, and for that you actually need a nuclear reactor because right now there's no fusion reactor built to test these superconducting magnets. So you use a conventional nuclear reactor to do that. So we do have MIT as a partner, because they'll do nuclear reactor testing. We have an entity called Ernie in Italy, and also a university in Vienna So these three institutions will be actually testing our materials by doing the neutron radiation testing. And we have a couple of the universities who will be doing some simulation and modeling to help us to guide us to develop a better material. And then we have a couple of companies to scale up and manufacture these materials into making into magnets.
Wow. Thank you for coming in and sharing this.
This is
No,
incredible.
happy to. Thanks for having me.
Yeah.
Thank you.
All right. Well, thank you very much. We have been speaking with Dr. Venkat Selvamanickam. He's a professor of mechanical engineering at the University of Houston. Dr. Selvamanickam, thank you very, very much for joining us on Hello Houston.
Thank you. Appreciate
Thank
that.
you. Now, we should have paid more attention in our physics classes.
Yes, we should.
We should have.